Matter is the stuff that makes up everything around us. Dogs, houses, and even tiny particles like electrons. But there's also antimatter, which can make up things like anti-dogs, anti-houses, or anti-electrons. How antimatter acts is an important question in physics. Does it behave identically to matter, or are the rules for antimatter and matter a little different? That is, if all our dogs, houses, and electrons turned into anti-dogs, anti-houses, and anti-electrons overnight, would anything change? At its core, this question is asking about symmetries. A symmetry is a change you can make to a system without making any observable difference to the outcome, like rotating a square by 90 degrees, or moving the entire experiment to the other side of the lab bench. So another way of asking if the rules are the same is to ask, is there a symmetry between matter and antimatter? One change that we can make to our universe is called C-inversion, where we change matter into antimatter and most properties, or quantum numbers, of matter to their opposite values, like electric charge. For example, when we change an electron into an anti-electron, it goes from being negatively to positively charged, which is why we call it a positron. If our universe isn't affected by a C-inversion, then we have a symmetry called C-symmetry. But it turns out that C-symmetry only works most of the time. One type of particle, the neutrino, causes some trouble. It's what physicists call left-handed, but its antimatter partner, the left-handed antineutrino, is nowhere to be found. Only right-handed ones exist. When we make our C-inversion, we also need to switch from left-handed to right-handed by flipping the direction of all our axes. We call this the parity or p-inversion. So maybe doing a C and a p inversion, called a CP inversion, is what we need to make the rules the same. If this works, we have CP symmetry. But in 1964, a famous experiment was done involving the decay of another troublesome particle, the kaon. These kaons can decay into two groups of particles, and one is the CP inversion of the other. So for CP symmetry to be true, the decay rate should be the same for each. But it turns out that one has a higher rate than the other. So even when we invert both C and P, our rules for antimatter are still slightly different. This can be resolved if we do something called a time reversal, or T-inversion. It might sound like something crazy out of science fiction, but it's best thought of as just changing the T into minus T in all of our equations. Most of physics is unchanged by this T-inversion, but for our troublesome kaons, this is not the case. The decay rates for the two groups get swapped. This means that kaons are neither CP symmetric nor T symmetric. Luckily, by doing all three inversions as a CPT inversion, these problems cancel each other out, and the rules are unchanged. In other words, if our dogs, houses, and electrons were to change overnight to anti-dogs, anti-houses, and anti-electrons, there wouldn't be any noticeable difference, as long as everything was C, P, and T inverted as well. If we make all of these changes, then the rules of antimatter shouldn't be any different to those of matter. This overall symmetry, CPT, is considered so fundamental and integral to modern physics that we'll have a lot of rethinking to do if it's ever proven wrong.